Alright, so welcome everyone to another science video lesson. Okay, so today we will going to discuss something which is very crucial in understanding the Earth's interior. Alright, so and also this lesson has something to do with in connection with earthquakes. So with that, alright, we will discuss today what they call the seismic waves. Alright, seismic waves are very important in studying the Earth's interior, and without them I think we will not be able to understand what are the composition of every layers of the Earth that we have right now. Alright, so let's jump in. Let's jump into the lesson on the other screen. So let's go. Alright, so here's the lesson that we have today, the seismic waves. So what do we mean by seismic waves? So these are technically these are mechanical waves. All right, so these are mechanical waves similar to your sound waves. Okay, and these seismic waves are released, all right, whenever there is an earthquake happening on land, right? So let's try to understand in this particular lesson. We will try to understand how they travel, all right, how they travel, what are the different kinds of seismic waves, okay, and what affects or what are the factors that affects the travel time of this seismic wave that we have right here. So let's get started. All right, so in this presentation, okay, so we have here the seismic wave. So as I've said earlier, this is a mechanical wave. Alright, and since it is a mechanical wave, it is composed of several vibrations. Alright, so it is composed of several vibration, and this vibration, alright, are somehow associated when they move through the earth. Alright, so these are waves that moves through the earth. So whether it is on the surface or inside the earth, it doesn't matter. It is called seismic waves. All right. So there are two kinds of seismic waves. So we will go over it one by one. All right. So at this point in time, we will start first on the first kind of seismic wave, and that is body waves. All right. So body waves are the key to identify the layers of the earth and what is the differences between, or what are the differences between the layers of your earth. All right. So what are body waves? From the word itself, body means inside, something like that. So it is generally a seismic wave that travel through the Earth's interior. All right, and it spreads outward, just like when you throw a stone on a water, it ripples. All right, it creates a ripples and it spreads, and that ripples spreads outward. Okay, and this seismic wave is distributed each in every corner portion of the earth. All right, in all directions. All right, so these are the body waves. And alright, so in this particular part, we will try to find out how we use the seismic waves, how do we use these seismic waves in order to find out that the Earth is made up of several layers. Alright, so let's have the first type or first kind of body waves. Alright, so the first kind of body wave is called the P waves. Alright, so in other books, this is called as the pressure wave. Alright, so as you can see, the movement of material, alright, so the one that you have right here, these are rocks. Right, so these blocks that you have right here is represented in real life. These are rocks, and as you can see, the rocks is undergoing compression. Alright, so the movement under P waves is back and forth, parallel. Alright, so the particle motion here is parallel to the direction of propagation. Alright, so as you can see here, the rocks expand and compresses, alright, vice versa, as the wave travels from one point to another. Alright, so what are P waves generally? So P waves, as I've said earlier, this is a wave that goes back and forth in the same direction as the wave movement. So it is parallel, and they can pass through rocks. Technically, they can pass through solids, and Also, not only for solid but also in liquid. All right, so they can pass through. All right, on those medium. Okay, so that is the P waves. All right, so the next type of wave that we have right here, underbody wave, is called the S wave. All right, so S wave, all right, is a type of wave that goes side to side, which is the movement of the wave is perpendicular to the direction of motion. So as you can see here, it goes up, it goes sideways over here. All right, it goes up and down. Then what happened here is, all right, what happened here is the material, the rock material that you have right here, jolts up and down. All right, so that is why this wave is also known as in other books as shear wave. All right, so as you can see here, the wave is doing a shearing action. All right, so shearing motion to the rock particle. So, all right, then if the P wave can pass through solid, so as the S wave, but the S wave cannot pass through liquid material. All right. So later on, we will try to find out what layer of the Earth, at what layer of the Earth does S wave cannot pass through. All right. Do S wave cannot pass through? Okay. So all right, the next kind of wave, aside from body wave, all right, the next kind of seismic wave, this is under seismic wave. All right, so the next kind of wave is called the surface wave. All right, so from the word itself, surface, I will not explain complicatedly the meaning of word surface. The word surface, all right, it means that this seismic wave travel on the Earth's surface. All right, so these are waves that cannot go inside the Earth. All right, it travels mostly on surface, and this is the type of wave. This is the type of seismic wave that we can feel during an earthquake. All right, so we can feel it on the surface. So it might be lab wave, or it might be a Rayleigh wave. All right, so as you can see here, right, so as you can see here, the lab waves is just like an S wave that moves side to side. All right, so side to side horizontally. Meanwhile, the S wave is vertically. All right, so this is horizontal movement, and this is perpendicular to the direction of the particle motion is perpendicular to the direction of the wave. All right, so that is the lab wave. Right. Next one. The Rayleigh wave is somehow very, I think this is very one of, if we will choose between these two waves, this is the most destructive because as you can see here, the ground rolls. All right. So the ground rolls, and what happens to the material? There is a force that goes up. All right. So as you can see there, and there is a force that goes down. All right. So that pushes down the rock, and there's a force that goes to the left, and there's a force to the right rather, and there's a force that goes to the left. All right. So if there's a structure that is built on this particular kind of ground, it will completely destroyed if it is not equipped with dampers or shock absorbers. All right. So that is the Rayleigh wave. Okay. So these two, the lab wave and the Rayleigh wave, are kinds of surface wave. All right. So surface wave is under seismic wave. So let's have a quick recap. All right. So seismic waves are vibration that travels through the earth. All right, that travels to the earth. It might be a body wave or it can be a surface wave. All right, so let's move on. All right, so the instrument that is called used in detecting these seismic waves is called the seismograph. All right, so later I will show you a picture of what a seismograph looks like. All right, so this is a very important tool in some geologists, right, and also with the volcanologists. Without the seismograph, they will not be able to identify the epicenter of the earthquake and the activity of a volcano or something like that. All right, so in a seismograph, all right, so the seismograph determines the velocity of your P and S wave. So make sure. All right, so I forgot some idea back on the first slide that P waves is faster than S wave. Right? So P arrives faster than arrive earlier rather. So P is faster than S wave. All right? So slower. This is slower, right, in terms of their velocity. And not only that, the P and S wave is affected by some factors in which they pass through. Alright, it can be a density of that particular rock material, or the rigidity, or in short, compactness of that rock material. Alright, so these two factors that you have right here affects how the P and S wave moves through the material. Alright, so the waves travel in more denser and more rigid material. So please take note of this one. So they travel in a more denser and rigid material. And in some cases, they are reflected. In some cases, they are reflected where there are different materials that they encounter on that particular area. So instead of going through, they are reflected somewhere else. Alright, so, and also, alright, those reflected waves are very important, alright, because it gives the seismograph an idea. Alright, it is received by the seismograph and it gives us an idea what kind of material is on that particular part. Alright, so very important that these waves must be captured by the seismograph in order for us to analyze this material. And not only reflect, alright, not only that waves reflect, also the waves refract. Alright, again, why do they refract? Because they, alright, if they encounter different materials, they likely to refract, or in other terms, they we call it bend. Yeah. So the wave bends. So why does the wave bends? Because these waves, when they encounter different material, that material likely to make the wave slow down. Alright, so it slows down that particular wave. Not only it slows down, so it also makes the wave go faster. All right, it depends upon the material. All right, so if the material is denser and rigid, it makes the wave travel faster. If the material is less dense and it is not rigid, it slows down that particular wave. All right, so the wave bends. All right, so if you are familiar with a pencil and glass of water experiment, the pencil is put inside the glass of water. So if you happen to notice, the pencil bends because the water slows down the speed of light. All right, so that's the reason why the pencil looked bent in that particular experiment. Same as the wave that we have right here. If the layer has different density, therefore it affects how the wave travels, especially its speed. All right. So these are basic idea. All right. So these are the basic ideas about the waves being captured or being analyzed by being captured by the seismogram. All right. So let's move on. Okay, in some industries like the petroleum industries, they use explosive. They use high explosive, and this explosive sets up seismic waves, that the one that you see here. And when they do, they allow this seismic wave to travel through the material, and if that material cannot allow the wave to pass through, it is reflected and then picked up by the seismograph. Then the seismograph is interpreted by a computer. Then the computer will analyze what kind of layer is on this area. Alright, so in modern times, in our modern technology, the computer now can create an image of this particular area just like an ultrasound. Alright, so on this area, in which they can map out the ground underground, they can map up underground in order to find oil, natural gas, and so on and so forth. All right, so this is what I'm talking about earlier, that the waves refract, all right, when they encounter two different materials when they travel. All right, so likely that this wave, all right, so likely that this wave likely to go faster. All right, so it goes faster because this material allows the wave to go or to travel at a maximum speed. All right, so in this particular picture that we have right here, Right? So in this particular that we have right here, the wave slows down. All right, because this material might be, it might tell us that it doesn't allow or it makes the wave go slower. All right. So with the use of the seismic wave, we can understand that these materials are two different materials which allows the wave to go faster or slower. All right. Okay, so as I've said earlier, that the waves, when there is an earthquake over here, so when there's an earthquake over here, it generates seismic waves and it doesn't only stays on one area. It is distributed all throughout different points on Earth, alright? Just like water ripples spreading outward. And these spreading seismic waves are picked up by seismograph on that particular area. So that is why an earthquake in Europe can be detected on a seismograph as far away as China, Philippines, or India, something like that, or even in US. All right, so it can be picked up by that seismograph. So that's the reason why the seismic waves are moving outward and they are spreading as it moves from the source of the seismic wave down to the that and goes outward. All right, so that is the earthquake that causes your that produces the seismic wave that we have right here. All right, so okay, so just a diagram that we have right here. So suppose this is the earthquake, and the earthquake generates seismic waves. It has surface wave that travels to the surface, the one that you have right here. All right, so the yellow one, and it travels outward, the same as your seismic wave, and or the same as your body waves rather. All right, and also we have your body waves. So we have P waves over here. All right, so there are some P waves that are very low in energy. They cannot pass through this particular area, which is the inner core. And there are some P waves that is high in energy that they can travel all the way to the core itself. So notice that the P waves are the only one that can travel through this area, because as we discussed earlier, that P waves, all right, that P waves can pass through liquid and they can pass through solid. Alright? Unlike S wave, they can only pass through solid medium like the solid mantle over here, but they cannot pass through the liquid outer core. And then it is reflected back, right? It is reflected back down to the surface of the earth. Alright? To be picked up by the seismograph. Meanwhile, the P waves will travel, alright? Will travel and it goes to the other side of the earth, then it will be picked up by the seismograph on that particular area. So as you notice that the waves refract, all right, the waves bend as they pass through different materials. So for example, like the one that we have right here, that P waves, all right, travel slower in liquid medium. All right, so in liquid medium they travel slower than in solid medium. All right, so with this, Alright, so with the use of your seismic wave, we be able to identify the different layers of the Earth and what is their dimensions. Alright, so the one that you have right here, that is their dimensions. Alright, so, or the thickness. Alright, and also, we be able to identify the density of these particular areas or the layers of the Earth. Alright, so, and that's because we use these seismic waves in order to identify them. Okay. All right. So it gives us that impression or that idea that as you go deeper down the earth, the more dense it is. All right. So the more dense, because there's a lot of pressure. There's a greater pressure inside the earth than the one on the outside. All right. So as you go deeper down the earth, remember the density increases. Right. The layers density increases. All right. So there we have other factors right here. So increasing depth. All right. Increasing depth, or as the seismic wave travel at increasing depth, the speed of this wave is also increasing. Because why is it? All right. Why is it increasing? Because the material gets denser as you increase in depth. All right, so therefore it is also increasing. And also, as you travel deeper, the pressure is also increasing. So therefore, the materials became more dense, all right, and therefore, the speed of the seismic wave also increases. Let's include also the rigidity of the material. The material is more compact as long there is a greater pressure. So the more rigid the material, the higher the speed of that seismic wave. But there's one factor that decreases the speed of the seismic wave, and that is temperature. But this is I think negligible. Alright, this is negligible because all of the other factors like depth, material, rigidity, and pressure are all increasing. Alright, so this is a negligible factor, so I think. Okay, so it decreases the speed of this seismic wave. Why? Because when you increase the temperature, the motion of molecules also increases. So it is difficult to transmit the energy from one molecule to another if they are spread apart. All right? If they are spread apart and they are moving faster. Right? The molecules is moving faster. So you cannot transfer the energy from one molecule to the other effectively. All right, so that is why the seismic wave is the seismic wave speed decreases as increasing temperature. All right, so these are the factors, and these are the effect of that factors to your speed of the seismic wave. Okay, so next, this is the seismograph. So as I've said earlier, so I will show you a picture of seismograph. This is the seismograph, and this is the needle and the drum. It contains a paper that can the needle will write down all of its recorded tremors on the earth. All right, so this is the seismograph. Right, so this is the seismograph at work. All right, so the one that you have right here, is the recorded seismic waves. All right, that passes through this seismograph. Okay. Alright, so these are the seismographs spread across the globe. Yan. So, in order for us to pick up, alright, in order for us to pick up all the seismic waves that is generated by an earthquake as far as this one or this one, alright, we will be able to understand and analyze them thoroughly because there are a lot of seismographs spread across the globe. Alright? So, next. Okay, so this is one example of seismograph reading. Alright, so okay, so later I will show you, or I will give you a particular YouTube channel in which you can watch the video on that particular channel in order for you to have an idea how to read the seismogram that you have right here. Alright, seismogram results. Yan. Alright, so as we can see here, alright, so earlier I've said that P wave travel faster than S wave. So here it is. So the P wave is the one that goes first in your seismograph. Alright, followed by the S wave. Alright, followed by the S wave. And followed by the... Alright, so this thing that you have right here, starting from this point. Alright, so the wave that you have right here are called surface wave. So the seismograph also picks up the surface wave, all right, passing the surface wave that is generated by your earthquake. All right, so as you can see, this amplitude, they are very very high, all right, in terms of amplitude. All right, so also the seismogram result, this seismogram result tells us also which place is farther away or near the epicenter. So the place that is near the epicenter is this one. All right. The place that is farther from the epicenter, it is the otherwise. The place that is near the epicenter is this one. All right. And this is near the epicenter, and this is far away from the epicenter. As you can see on the amplitude of the P and S wave, All right. So on this particular area, on this particular location, the amplitude of P waves is higher than the amplitude of P waves on this particular location. So there's a difference in amplitude, the one that the spikes over here, and also with the S wave. All right. So again, we can identify how far the area away from the epicenter by the use of your seismogram results. Okay. And also with your seismic waves, like with your seismic wave, the P wave and then the S wave, we be able to identify that the Earth is made up of two layers of core. All right. So we have the core is made up of two layers. So we have solid inner core and the liquid outer core. And that is because of these particular zones called shadow zone. So as you can see here on the diagram, the P wave shadow zone is a part, all right, it is an area on Earth that is 103 degrees and 142 degrees on arc, in which there are no waves, there are no P waves passing through. Now, what is the reason why there are no P waves passing through? It's because the waves are refracted as they pass through the liquid outer core. Right? So as they pass through the liquid outer core, it is refracted and then it goes back again to its usual speed as they move out that particular liquid outer core. Alright, so that is why we have a P wave shadow zone on this degree of arc that you have right here. Alright, not only that, but also an S wave shadow zone. Alright, S wave shadow zone is larger than P wave shadow zone. It starts around 103 degrees of arc on this side, and it goes to another 100 degrees of arc to the other side of the Earth. Alright, so why is it? Because the S wave cannot pass through liquid, so that is why it creates this large area where there are no S wave that can travel. Alright, so then what happens on this wave that you have right here? It is reflected. Alright, so this wave is likely to be reflected, right, because they cannot pass through the liquid outer core. Alright, now because of the S wave and P wave respectively, we be able to identify that the Earth is made up of two cores. Right, so our inner core is solid and the outer core is liquid. Alright, so thanks to this seismic waves that we have right here. Alright, so with that, okay, with that, in order for us to use, or how do we use these seismic waves? All right, in what application can we use the seismic wave? One application is we can identify the epicenter of an earthquake. We can identify the epicenter of an earthquake using seismic waves. All right, so we called it the earthquake triangulation. You need three seismic station in order to pick up to predict accurately which or what is the area or what is the location of your epicenter. All right, so for you to be able to be guided by that, all right, so I recommend, to for you to visit the channel of Mike Sammartano. All right, and he has a video. All right, he has a video here that explains the earthquake triangulation, the one that we have right here. Okay, so just visit his channel and subscribe on it as well. And also, he will also teach you how to read the seismogram analysis. Okay? So this is very I recommend this one. This is very he discussed this seismograph reading and how to use them in a very superb detail. All right. So just go to his channel on YouTube, okay, and watch this two video, the earthquake epicenter triangulation, okay, and the seismogram analysis. If you want to discover how can we use the seismogram analysis to predict the epicenter of an earthquake. All right. So with that, Okay, that ends up our lesson this on this day, and I hope you did get something from it. So if you value this lesson, just give it a thumbs up on this video. Just hit the thumbs up on this video, and if you want to be notified with another or with a video like this one in the future, you just click there the subscribe and the bell button on that subscribe area. All right. So if you have some questions, don't hesitate to write down in the comment section. All right. So well, that's it for this video. So I hope to see you next time. Right. So peace out, everyone.